In my previous video, I showed how to use an electric meter and a heater to find the relative position of electrical outlets on a circuit. Today, I'm going to outline the basics of the theory, why this technique works. If you're just interested in a how-to without understanding, you may want to skip this particular video, but I recommend that you understand what you're doing. It can help to prevent mistakes and give you more satisfaction in the job that you're doing. So in North America, you will see electrical outlets that look something like this. This has two plugs in it. The first plug, each one of the plugs has three connections. You'll notice that one of these is wider than the other, and then one of them is round. The narrow one is called the hot pin or the hot connector. The wide one is called neutral. And the round one at the center is called ground. All right. We'll look at why they're called these things. If you take one of these apart, which I'm not particularly advocating and we don't need to do at the moment, you'll see that these pins are connected to terminal posts. Which this is a Canadian outlet, and you can see that these terminal posts can actually be screwed with either a flat screwdriver or a green Robertson screwdriver. For my unfortunate American friends who rarely have find Robertson screws, these will probably be dual flat and Phillips. Phillips is terrible, as is flat. Well, I don't know, choose one. I think flat enables you to get better torque on the screws than Phillips does. Anyway, I diverge from the theory that I'm planning to present. The basic thing is that each of these slots in the receptacle is connected to one of these terminal posts. So the neutral is connected to the silver colored terminal posts. The hot is connected to these copper colored or brass colored terminal posts. And the ground is connected to a green, or in this case, I think this was green once upon a time, a green terminal post. Okay, and those are connected to wires, and those go off to, through your walls or your ceiling, and they're eventually connected to the electrical utility. So how are those connections made? That's really the subject of today. So here's a picture that I've drawn. The colors that I had very carefully done don't show up particularly well on this video. I'm hoping that on the recording they'll be a little bit more visible. Anyway, you probably buy your electricity from an electric utility. If you don't, well, pick your windmill or solar or whatever your source is. If you have electrical wiring in North America and it's according to code, that electricity will come in to a service panel. A service panel, sometimes known as a fuse box or a breaker panel. The electric utility is delivered to you over three wires, one red, one white, and one black. The white is the so-called neutral wire. And the red and black are both different versions of hot wire. If you have a house or a townhouse or something where you buy your electricity directly from the utility, it almost certainly comes in like this. If you're in an apartment building or an industrial building, you may find it slightly different, but the basic idea is the same. Basically, between the red and the black wires, you have 240 volts. And some of your appliances, like your dryer or your range or your air conditioner, will probably use the full 240 volts, but normal electrical outlets and lighting uses only half. So it either uses the 120 volts between the neutral and the black, or the 120 volts between the neutral and the red. When you look at an outlet like this or this or this, you can't really tell in any obvious way whether it's connected to the black side or the red side of your electrical service. They try to make them about half and half. Anyway, if you really care, you can find out, but for the most part, we don't really care. All right, so when these three wires come into your breaker panel, your service panel, basically they are connected to big copper bus bars. And you know, the center one is neutral and one is the black side and the other is the red side. Now the neutral is also bonded, it's connected to ground. Okay, so neutral is going to be connected to any electrical box that is involved in this circuit, and it's also going to be connected, you know, to your water pipe or something like that, that is going to actually make it connected to the actual physical earth. Then if you want to wire up some outlets or lights, you connect a breaker into the breaker panel, and the breaker can go on the black side or the red side, it doesn't matter. But what happens is the breaker has two connections in it. One connects to the neutral, and that will come out as a white wire. I can't draw white on a white piece of paper, so I've colored it blue. And, you know, from my looking at my monitor, you can barely see, but this is blue, which is meant to mean white. And then connected to the hot side is a black wire. And this black wire is going to be connected to the narrow slot on your electrical outlet. So this black wire goes to the narrow slot on this electrical outlet and also the narrow slot on that electrical outlet. The white wire is connected to the wider slot. That's always the case. That's so you don't accidentally stick, you know, a big, if you have a big plug that is meant to go in the neutral, it won't go in the smaller slot. So you can't get hot where you are expecting neutral, unless of course someone has miswired this outlet, which happens more often than you might think. Then finally, from the service panel box, bonded right to the neutral, you have a separate wire. This wire is typically green or just bare copper. It's not insulated at all. This is a separate ground wire. So in some ways it carries the same thing as the neutral, but things get different when there's a problem with the circuit or when the circuit is under load. So anyway, we have any number of outlets. You can see in this diagram, the breaker box or the wire from the breaker goes first to this outlet. This direct connection from the breaker to the first outlet is called a home run. And in general, if we want to install a ground fault or arc fault box, we want it to be connected to the breaker box by a home run. So we want to figure out that this outlet is connected to the home run and this one is not. Anyway, we have two outlets here. The grounds are both connected directly or indirectly, and the hot and the neutrals are all connected to the breaker. Now here's another outlet that may be somewhere else in my house. Notice it's connected to a different breaker, happens to be on the red side. Even though it's on the red side, we typically still use a black wire in order to connect it from the panel to the breaker. And again, we use a white wire for the neutral. and a green or unshielded, uninsulated wire for the ground. Okay, so what happens here? So as I mentioned last in my previous video, if we have an electrical meter, we can set it to 200 or 250 volts maximum, and we can start measuring the difference between different wires. So if we take our electrical meter and measure the difference between these two wires coming in, we will find this is 240 volts. If we measure the difference between here and here, the red and the neutral, that will be 120 volts. And the difference between the black and the neutral will also be 120 volts. Those same differences are carried all the way down these bus bars. So between this bus bar and the right bus bar in the center is 120 volts. Between the left and the center is 120 volts. And between the two is 240 volts. All right, so this is the situation that happens when there is no load, when we don't have a heater or a toaster or anything else plugged into these outlets. You can see that the red, because the narrow pin is connected to neutral, and the small pin is connected to hot, and the wide pin is connected to neutral. If we put our meter across those two pins, we will see 120 volts. That's also true if we do look at this outlet. That's 120 volts. And so is this one, 120 volts. This is all with no heaters, no load plugged in. Well, let's do a couple of other things. Supposing we measure the difference between ground and the narrow pin. That's also going to be 120 volts. Right? Because ground goes through the box, it's bonded to the center, and the hot is 120 volts away from there. If we take ground to the wide pin, that's going to be 0 volts. So there's, in this ideal situation, what happens is we have no, there is no voltage between ground and the neutral. Now, if we plug in a heater, it will be difficult for me to plug in a heater to my paper here, but why don't I draw a picture of a heater and draw it in. So here's a heater. And it has a plug. And its plug obviously has 3 prongs. And I'm going to plug it into this outlet. So what happens is when I plug my heater into this particular outlet, it starts drawing current. It draws electricity from the hot, and to use a bad metaphor, it draws the electricity from the hot and it goes through the heater making heat, and it comes back through the neutral. Once there's a load here, there is a voltage drop. The voltage between this pin and this pin is no longer 120 volts. It's something smaller. Maybe it's 117 volts, and that would be a 3 volt voltage drop. We will also notice at the same time, so let's suppose that this voltage is 117 volts. This voltage might be 118 volts. Why? Well, this voltage drop occurs continuously along the wire. So if the total voltage drop between both these wires is 3 volts, if we're only going about 2/3 of the distance, the voltage drop will only be 2/3 of that, which is maybe 2 volts. So that's what happens when I plug a heater into my circuit. If the heater is plugged into into a downstream outlet. Now let's continue that a little bit more. If this voltage is 117 volts, it means we lost 3 volts somewhere. We lost 3 volts. If our electrical system is in good shape, we will have lost those 3 volts equally on the black hot wire and the white neutral. So that tells us that actually, if I measure the difference between the black and ground, I should get 118.5 volts, because only half of the voltage drop is between the hot and ground. If I measure the voltage between ground and the neutral pin, lo and behold, we're going to have 1.5 volts. So the voltage drop is shared equally between increasing the voltage on the white, the neutral, and decreasing the voltage on the black. And this actually gives us a very good way to check the health of our electrical system. If we have a bad connection somewhere, it will typically have a higher voltage drop across it than it should, and that could easily lead to a fire. If you ever see that the difference between ground and neutral is different from the difference between the hot and what the hot would be without a load, then you can see that there's a problem in your circuit. All right, so let me do one more thing, and then I'll call it quits for this particular video. Suppose we plug our heater into the bottom outlet. We plug our heater into the bottom outlet, we will see a certain voltage drop here. Maybe it'll drop to 118 or 119 volts. Same thing applies. Half the drop should be here and half the drop should be here. So let's suppose this drops to 119 volts. If I then measure the voltage here, it will be 119 volts, because there is no load between here and here, and therefore there's going to be no voltage drop between this outlet and this outlet. So they'll both be 119. And that's the basic theory of why we can just measure voltage drop in order to determine our distance from the fuse panel. One last thing. Supposing I connect my heater to this outlet. Well, the voltage drop to this outlet might be 118 volts. Or the total voltage might be 118 volts. What happens to these ones? Well, these ones, I would say they're not going to drop at all, but that's not quite true. Because when you put any voltage on, you're actually going to be pulling electricity from the breaker from the utility. And along all these lines from the utility and stuff, there's going to be a slight voltage drop as well. So you might find that when you plug in an outlet here, that these two will drop from 120 to 119.6 or something like that. You know, the half a volt drop, or probably less than half a volt drop. If you're seeing that, it means that probably these are connected on different breakers. So you'll get a voltage drop here, but not, at least not a substantial voltage drop on any outlet that is connected to a different breaker. Okay, that's the end of the underlying theory. In my next video, I will return to the how-to of how to build a table of all the voltage drops and how to deduce what the connections are in the walls and junction boxes and lights and outlets and breaker panel, so that you can figure out where the home run outlets are. And that's where you should install your circuit interrupting devices.